Okay, welcome back. We're going to keep going on this book. In this section, we will introduce some key concepts and terms frequently used when discussing ML, machine learning. Frequently, when discussing with vendors or other stakeholders, terms such as supervised or unsupervised learning, clustering, or regression, among others, may be mentioned. I want to ensure you can put the proper context for all these concepts. This section aims to build a good understanding of what those terms mean. Types of problems to be solved with ML. Let us start by evaluating, in a general way, what ML is for. And we've already, earlier in the book, they said it is for automating decisions rather than actions. What are the types of problems ML algorithms are designed to help with? Once we identify them, it is easy to map the same to clouds and networking, and you will likely identify pain points in your infrastructure where some of this could be helpful. While I am not trying to be completely exhaustive, we can group the types of problems ML can solve into the following categories. Classification problems. There is a set of categories, and you want to assign or determine which category or particular entity, or determine which category a particular entity belongs to. Examples of this type of problem are classifying an image of a tumor as benign or cancerous, classifying objects on an image, and determining if a tweet is positive or negative concerning a specific topic. These are all examples of classification. In networking or IT, you may want to classify whether an email is spam, alternatively, whether a specific traffic pattern corresponds to a DDoS attack, or you may want to classify your Wi-Fi network users based on their device type. Prediction or regression problems. While in the classification problems, what you are trying to obtain from your input data is the assignment to one out of a discrete set of categories or classes, regression problems are about deriving a certain number from a continuous space given such input data. You want to forecast the sales next month or predict the temperature tomorrow. These are types of regression or prediction where the input may be a set of variables and the output is a number from a continuous space. In networking, we can easily find use cases for regression. If you want to predict the memory utilization in a router, given a set of input variables such as the number of subscribers, number of routes, configuration size, and maybe others. So regression is the big one. Regression is the one where there's a lot of use cases in networking. Let's go back over what regression is. So this is prediction or regression problems. And I'm just going to read this whole thing again. My mind was kind of wandering. I did that thing where I read it and I don't remember having read it. Prediction or regression problems. While in the classification problems, what you are trying to obtain from your input data is the assignment to one out of a discrete, so like a finite, a limited set of categories or classes. Regression problems are different. Regression problems are about deriving a certain number from a continuous space, such as input. So that's different from a discrete set. So with the classification problems, you're dealing with a discrete set. But with regression problems, you're dealing with continuous space. So there's no limit. It's an infinite. If it were input data, it would be an infinite stream of data. You want to forecast the sales next month or predict the temperature tomorrow. These are examples of regression or prediction where the input may be a set of variables and the output is a number from a continuous space. So, it's unlikely, but the temperature tomorrow could be infinity plus 1. So that's a continuous space. There's no end to numbers. You can just always take the final number and add it by 1. So that's a continuous space. Whereas days of the week, Monday, Wednesday, Friday, is a discrete space. There's only 7 of them. So in networking, we can easily find use cases for regression. And remember what regression is. Regression is from regression is kind of like a prediction. So you want to predict the memory utilization in a router given a set of input variables, such as the number of subscribers, number of routes, configuration size, and maybe others. That's actually a really good use case. So basically what you can do is, interesting. Do you know what's really cool about that actually is like cloud networking, the main advantage you get is that pay as you go pricing, and like the main scenario that they say is bad is you overspend and now you have or you over or underspend, either one. But you could make it I feel like you could do that a lot better with AI, with machine learning techniques, a subset of AI. Like using AI in your network, you can make better decisions about what sorts of cloud services you actually need. Clustering problems. In this type of scenario, you do not know precisely what categories your data is grouped into, but you somehow know or have the intuition that there are some groups in your data with certain commonalities, and you would like to identify these groups, clusters. The goal is therefore to extract internal structure from the data and identify those clusters. Additionally, identify which one each data point belongs to, if any. Examples of this type of problem are identifying groups of people by their purchasing practices, input data. In networking, for example, you could identify clusters of users or subscribers based on specific behavior patterns, or you could cluster devices together based on certain metrics collected and auto detect the role they have on the network. Oh, that's a good one. Yeah, so you can see what people are doing on the network, and you can cluster them in, and then you see like, oh, this person has been doing all this extra stuff that they weren't meant to. Like, what's up with that? So you could kind of see when something breaks out of the mold. That'd be great for security, because it's like you can see when something's happening in a way that is unusual. Optimization problems. I refer to this category as optimization problems because they are all about improving or running specific processes more optimally. In that task, it is required that some entity can learn what needs to be done and what are the consequences of each action executed, and can close the loop considering certain optimization targets. Examples of this type of problem are playing Go or chess, or the car cruise speed control. So your speed control, your cruise speed control in your car is an example of an optimization problem. Yeah. In networking, we could find problems like this, such as optimizing BGP peering traffic or optimizing QoS in the network, or SD-WAN tunnel utilization, to name a few. Generation problems. Given a particular input, it is necessary to generate new data. Generating new fake videos, fake or photos is an example in this category. Also, generating new text or summarizing one existing text would be examples that fit this category. In networking, we could also find generation problems around generating new traffic data for the lab, generating new configurations for network devices, or creating an incident summary out of several individual alerts or log messages. Wouldn't that be cool? It's like you can build a better picture of your that would be cool. So you could generate a architecture. You could generate a plan, a way to build out the network. Like you could generate reports or recommendations for like that. I feel like generation is like particularly something kind of cool. And then like the configurations, you can generate the configurations, have the devices configure themselves based on the automated decisions. All right, next section is the art of modeling. Before we dive into the different types of machine learning techniques, I think it is essential to understand that machine learning projects are a bit of an art of trial and error. I know I have not introduced the different techniques yet, but ultimately a data science engineer has a toolkit of options, algorithms to solve a certain problem. For each algorithm, there are several parameters to fine-tune. They are referred to as hyperparameters. For a particular problem, various algorithms could be valid. That is the first choice that must be made. Then the selection of adequate hyperparameters will be required. For most of these decisions, there will be a component of experience and intuition about what may or may not work for such a type of problem. But primarily, there will be a strong component of trial and error. Machine learning is a field of trial and error, especially in selecting the hyperparameters for the algorithms. Most of the time, the impact of those hyperparameters is not going to be linear or even deterministic at all, and a slight variation in one parameter might lead to a completely different result or even lack of convergence in the algorithm. I am not trying to scare you with this, but just state that frequently the results will be obtained after trying multiple options, which only reinforces the message I gave you earlier in the book. Brute force is your friend. For many years, trying all these options required the data science engineer to test many combinations of parameters or algorithms manually and iteratively. Fortunately, there are libraries and frameworks in what is referred to as AutoML that will automate such processes, automatically trying all the different algorithms and hyperparameters in more efficient ways. Still, brute force is required. I will not enter into detail on the different AutoML techniques, as my intent is not to provide optimal models in the use cases illustrated in the book. There is plenty of literature available about AutoML and how it can be used in combination with the different algorithms we will describe to build optimal pipelines for a particular use case. Key takeaway: experience will help you build the intuition about what works and what does not. Meanwhile, you can use AutoML techniques if you need to build an optimal model. Types of machine learning techniques. We have reviewed in the previous chapter what type of problems machine learning techniques can address. Now let's focus on what types of machine learning techniques exist. This section aims to give you a quick overview based on a well-defined classification scheme. We will dig deeper into specific examples of techniques or algorithms in the subsequent sections as we navigate through actual use cases. One common approach to classify machine learning techniques is based on the need or the lack of to have labeled data. However, what are the labels exactly? A label is a particular property or value associated with the input data available for a problem. When such a label exists, we can use the existing data to build machine learning models that will allow us to predict the label for new input data for which such a label may be missing. Those labels serve as examples to build our model. Examples of labeled data: a data set of emails and whether each email is spam. A combination of input parameters for a router configuration, number of VRFs, virtual routing and forwarding. The F's just means that's plural. It's kind of a weird acronym to have in plural. Number of interfaces and number of VLANs, virtual local area networks. And the memory consumed. The memory consumed is the label. Yeah. In all those cases, there is some input data and some output, the label, which we would like to predict or identify for new incoming data. However, such labels are frequently unavailable, and we only have an input data set. In the example above, input emails, but no label on whether the email is spam or not. And you can't apply that label until the email is received and analyzed, which puts you a step behind already because you'd rather they just not send spam in the first place. There are no reference observations we can use to identify their spam nature. In this case, this is an unlabeled data set. Based on the existence or not of labels in the data, machine learning techniques are grouped in unsupervised learning techniques. They do not use labels. Their mission is to find knowledge or structure in the data itself. The fact that we do not have labels in the data means we know very little about it. The purpose of the machine learning algorithm is to extract information from within the data itself. We will review the specific categories and examples of algorithms in the following sections. All right, so the next machine learning technique group. So the first group of machine learning techniques was the unsupervised learning group. The next one is the supervised learning group. So these are supervised learning techniques. Depend on the existence of labels. The assumption for these is that the incoming data has labels, and those labels will be used to guide the algorithm in learning. The model builds knowledge based on the existing data and labels. Such knowledge is later used to add labels to new incoming data. So the next category of machine learning technique is reinforcement learning. In this case, data does not exist in advance for practical purposes. These techniques are applied where we want some agent to learn the proper actions to do in a specific environment. The learning process will be based on the rewards produced by such an environment as the actions are taken. In simplest terms, the agent will generate experience by making mistakes and learning from them while executing a particular task. As you can see, there is no previous data, labeled or unlabeled. Data will be generated for the learning process as the agent executes actions. We will see more detail on these techniques later in the book. Oh, I would love to do some of that on my home lab. That would be amazing. So the next and final category of machine learning techniques is the self-supervised learning techniques. While I think it is effectively a subcategory of the supervised techniques, you may find it frequently differentiated. It is a growing area of interest. Supervised learning requires, by definition, labeled data. Getting labeled data is expensive in many use cases and is subject to human error or biases. Usually, the labeling process is executed by humans, which is expensive. In that context, and particularly in areas such as natural language processing, NLP, and others, there are many use cases where the label to use could possibly be the next data point on a sequence, the previous one, or a particular data point within that sequence. Ultimately, the data point used as a label can be extracted from the data itself and used to train a supervised learning model, much like any other supervised approach. Therefore, as you can see, it is effectively a hybrid between an unsupervised technique. Okay, so it's a hybrid between an unsupervised technique. In practice, the available data is not explicitly labeled, and we will extract knowledge from it. However, in its execution, it is a supervised learning technique because the model's training process uses a label that happens to be extracted from the incoming data. We will see some practical examples of it. As referred, NLP is a field that has experienced significant progress by using these techniques. NLP stands for Natural Language Processing. And some argue that the future of ML, machine learning, will be mostly based on self-supervised techniques. The reason is that labeling data is expensive, and the next generation of use cases will require 1 or 2 orders of magnitude more data. Therefore, depending on human labeling may render them impossible. Yeah, so the more data, because right now I've actually heard stories of human labeling that perhaps violate some ethical standards. But as the data becomes bigger and bigger, the human capacity to go through it, assign it labels, will become smaller and smaller. Key takeaway: machine learning techniques are simply tools in a toolkit. Much like protocols like OSPF, BGP, are tools in your network toolkit. None is fundamentally better than the others. They simply have their field of applicability. I would really like to do reinforcement training. So we're going to go through each of these categories of machine learning techniques in more depth. We're going to start with unsupervised learning. And let's check the time here. Let's try to get through this one. I think I can do it. I'm kind of don't have a lot of energy, but let's do it. As mentioned earlier, these are the techniques where we do not have labeled data. That means all we know and can assume from the data is in the data itself. What type of techniques will we find in this category? Let us review them. Clustering. Clustering is a term that you may be familiar with. It is about finding clusters or groups. And remember that was so it's about finding clusters or groups, which is something that sounds very much to me like a clustering problem. So in this type of scenario, you're trying to put them into groups. The notion of a cluster implicitly has a sense that certain entities have something in common, and they therefore belong together. When we cluster entities from a data set, we are extracting structure from the data itself. In this case, learning how they group together. It is very likely that during that process, some observations may not fit in any cluster. They should be identified as outliers. There are multiple clustering algorithms. We will briefly describe some in this section, and there will be a practical use case later on in the book. However, before that, we must explain some key concepts that apply to all of them and apply to other techniques. When we use the term cluster, we somehow imply that some of those data observations will be closer or more similar to each other than others, and such similarity will determine its belonging to a specific cluster. However, how do we measure similar or close? There are multiple ways. How can we tell whether or not they belong in the same cluster? There are multiple ways, and none is fundamentally better than others. It really depends on the use case. Let's suppose our dataset consists of observations of the following data points from your top-of-rack switches in the data center. Each observation has the following content: the number of ports used, number of VLANs used, number of VRFs, and number of ACLs, access control lists. We have, therefore, 4 variables for each switch. It is a 4-dimensional space. The following diagrams will only show the first 2 dimensions for visual representation purposes. Each dot in the graph represents one switch in the network. As can be perceived just by observing the graph, our human intuition identifies probably 3 clusters. Nevertheless, how do we get an algorithm to detect that automatically? First, as mentioned earlier, we need to define some way to measure the distance between the different observations and evaluate which ones are closer. There are various types of distance used in the context of machine learning algorithms. So we've got a graph here. We've got the number of VLANs used, and we've got the number of ports used. So as the number of VLANs used increase, this is interesting. I actually don't really know what this graph means. So we've got some math stuff here. So we explain it. So we've got the number of ports used, number of VLANs used, number of VRFs, and number of ACLs. So there's the number of VLANs used, number of ports used. I don't see the number of VRFs and number of ACLs. But we have 4 variables for each switch, a 4-dimensional space. We're only going to focus on 2 dimensions. Each dot is going to represent a switch. So here we have a switch in the network. This switch has not that many VLANs, but it has a lot of ports. Here we have more switches. This one here in the center has a lot of ports used and a lot of VLANs. And then this one here has very few ports used, but a lot of VLANs used. Okay, so Euclidean distance. This is the traditional and most well-known method for any engineer to calculate distance between two n-dimensional vectors. So hopefully this you know what? I'm gonna say it. I honestly hope that somebody watching this right now doesn't know what this is and has never had any experience with that at all, and this is your first experience. If that is you, go to ChatGPT, the free tier, and say, in the context of... So, explain, in the context of Euclidean distance, and I'll start it. In the context of Euclidean distance, explain the most well-known method for any engineer to calculate distance between two n-dimensional vectors. And you don't have to say it out loud. Just copy paste it in there.
The most well-known method for calculating the distance between two n-dimensional vectors in the context of Euclidean space is the Euclidean distance formula. This formula is a generalization of the Pythagorean theorem to higher dimensions.
Yeah.
For two vectors,
just jump on ChatGPT. You don't even pay for it. Go for the free version, and there you go. This is boring. I hate this. Rewrite it and teach it to me as if it were a Batman TV show. Yeah.
Alright, Med and Gotham City, a sprawling metropolis filled with towering skyscrapers and shadowy alleys. In the city, our heroes, Becker Man and Distance Woman, are on a mission to calculate the distance between 2 points in the heart of the urban jungle.
Yeah, so you get the idea. If you don't like it, change it. If you do like it, go in deeper. Like, you've got a huge advantage here. Like in school, you'd have all these other subjects you've got to get through. You have 2 weeks at most to get everything done with this course before you move on. So if you don't understand it, then you're SOL. So I honestly hope anyone who might watching this series and sees this and has never heard about this, get on. I hope there is somebody like that, because this is such a unique time in history. Just jump on ChatGPT 3, go down the rabbit holes, have it, explain it to me like I'm a fifth grader, explain it to me like I'm, and you can learn this stuff now. I honestly believe we're in the first wave of the AI revolution is personalized tutoring. I honestly believe that's what we're in right now. Okay, so Euclidean distance. So we can see there's the what was mentioned in the response here. This is the Euclidean distance formula. Okay. In a more general way, the calculation for Euclidean distance is this. And again, please, I beg you, do not get scared of. Well, first of all, if you're watching this and you're a math whiz, then you're fine. But kind of this channel is meant for people like me who either when they were doing math was decent at it, or people who just never really had a chance to learn high level math. That's kind of who I'm most excited to reach through this channel. And if I'm talking to that person right now, go to ChatGPT. Now, we can see here, you can't paste in screenshots when it comes to ChatGPT 3, the free version. If you pay $20 a month for the paid version, now you can paste in a screenshot. So now that I've done that and I hit enter, it'll tell me more about this.
This formula represents the Euclidean distance between two vectors in n-dimensional space. The Euclidean distance is the straight line distance between 2 points in Euclidean space, which is the geometric space that most people are familiar with. The formula is used to calculate the distance between 2 points, or vectors, AAA and BBB, where each point is represented by a vector of values. Here's the breakdown. N-area summation. Sum n-area summation denotes a summation over a set of elements.
All right, so use more common, colloquially known language rather than mathematical language and symbols to explain this to me more clearly. Help me get used to the symbols and the things you are saying, even if I've never seen them before.
Imagine you're playing a game where you have to draw a straight line between two dots on a piece of graph paper, and you want to know how long that line is. The formula you've shown me is like a super accurate ruler for measuring that line, but instead of just on paper, it works in a space where you can have many more directions to go than just left, right, or up, down, like a 3D video game world, or even more complex. So, in our game, let's say each dot is actually a bunch of points stacked up, kind of like a list of how far each point is from a corner of the paper in different directions. The formula is saying, for each matching pair of points in the two lists, see how far apart they are by subtracting one from the other. If the difference is negative, just ignore that and make it positive, because we only care about how much distance there is, not which one is ahead or behind. After you've done that for each pair of points, you square that distance. Squaring is just multiplying a number by itself. It's like saying, if the points are a little bit apart, it's not a big deal, but if they're really far apart, let's make that count for a lot more. You do this because you want to give more weight to bigger differences. You add up all those squared distances into a big total. Then, since we squared things earlier, we have to take the square root at the end. That's like making sure our ruler's measurements stay consistent. The square root just undoes the squaring we did before, giving us the straight line distance between our two dots that takes into account all the different directions they're spread out in. In simpler terms, if you were telling a friend how to walk from one place to another in the city using this formula, you'd be giving them the shortest path they could possibly walk, no matter how many turns or hills they had to go up and down. It's a way to make sure the path is as short and direct as it can be.
Does squaring have to do with the square shape?
Yes, in a way, squaring a number is related to the idea of a square shape. Here's a connection. Imagine you have a square piece of paper. The length of one side of the square is, say, 4 inches. Now, if you wanted to find out the total area of that square piece of paper, you would multiply the length of one side by itself, because all sides of a square are equal. So, 4 inches multiplied by 4 inches gives you 16 square inches. That's the area of a square. The operation you just did, multiplying a number by itself, is what we call squaring. So, when you square the number 4, you get 16. It's like you're making a perfect square on graph paper using the number of units on each side. In the formula you showed, when we square the differences between the points, I minus by 2, a underscore I, b underscore I, squared, I minus by 2 part, we're not literally making square shapes. Instead, we're making sure that the differences are all positive, since area can't be negative, and we're also giving more weight to larger differences, just like a larger square has more area. So, squaring a number is an operation that has a visual representation, the area of a square, and a practical application, ensuring positive values and emphasizing larger differences.
What is the insane, crazy, galaxy brain, stupid, difficult, complex, mathematical string theory thing associated with this that you could only learn if you had like 7 PhDs?
What you're talking about could be related to string theory, which is a framework in theoretical physics where instead of point-like particles, everything in the universe is made up of tiny, vibrating strings. It's a candidate for the theory of everything, an overarching description of the fundamental forces and particles in the universe. Here's a taste of the kind of math you'd see in string theory. Gauss manifolds. These are complex, multidimensional shapes that are possible shapes for the extra dimension string theory says the universe has. The math behind these shapes is incredibly intricate, involving advanced geometry and topology. Quantum field theory, QFT. This is a mathematical and conceptual framework for contemporary elementary particle physics. It combines classical field theory, special relativity, and quantum mechanics, and it's notoriously difficult, even for physicists. Supersymmetry. This is a principle that proposes a relationship between two basic classes of elementary particles, bosons, which carry forces, and fermions, which make up matter. The math of supersymmetry is deep and involves advanced algebra and representation theory. Conformal field theory, CFT. This theory applies to various systems at critical points and has deep connections to statistical mechanics and quantum field theories in different numbers of dimensions. It's a key part of the mathematical structure of string theory. Path integrals and partition functions. These are ways to sum over all possible histories of a system. They're used in quantum mechanics and quantum field theory and involve some seriously high-level calculus analysis. String theory is at the edge of our understanding of physics and requires a blend of quantum mechanics, general relativity, and high-powered mathematics. If it sounds mind-boggling, that's because it is. It's a real challenge even for those with more than one PhD.
Is string theory stupid and weightless and wasteful and a waste of people's time and energy who could instead be working on more imminent and pressing problems such as aligning AI and other sorts of problems, perhaps even climate change?
The value of research like string theory often comes under debate, especially when considering the pressing global challenges we face today. Here's how to think about it. Pros of fundamental research, discovery and knowledge. Fundamental research enriches our understanding of the universe. It's about asking why and how without knowing if there's a practical application. Unforeseen applications. Many scientific breakthroughs, like the internet or GPS, were byproducts of research not aimed at creating them. Inspiration. Advanced theories like string theory inspire new generations of scientists and capture the public imagination. Cons of high concept research. 1. Applicability. Critics point out that theories like string theory have yet to provide testable predictions or tangible benefits. Balancing priorities. In an ideal world, we'd have enough resources to tackle all problems simultaneously. However,
Is it true that string theory has yet to provide testable predictions or tangible benefits, or is this claim false? Evaluate this claim. And I'm on a tangent here. I apologize. I'll try to get back to the scheduled program. This is why I don't get things done.
the claim that string theory has yet to provide testable predictions or tangible benefits is, to a large extent, true, and it reflects one of the major criticisms of the theory within the scientific community.
Damn it.
Here's why. Testable predictions. String theory, in its current form, requires energy scales and precision and measurement that are beyond our current technological capabilities to test directly. The theory suggests the existence of additional dimensions and other phenomena that are not directly observable with today's instruments. Some physicists argue that string theory is not falsifiable, a key criterion for a scientific theory, because it's difficult to think of an experiment that could prove it wrong. Tangible benefits. Unlike theories that have led to technological advancements, like quantum mechanics leading to semiconductors and, by extension, computers, string theory hasn't yet resulted in new technologies or applications. Its contributions have been more philosophical, providing a potential framework for unifying the forces of nature, though without empirical verification so far. However, it's important to note a few points in defense of string theory and fundamental research. Indirect contributions. The development of string theory has led to advancements in mathematics and related fields. Concepts from string theory have provided new tools and methods in mathematics. Theoretical work can lead to unexpected applications. The history of science is full of examples where esoteric and abstract theories have much later led to groundbreaking new technologies. Philosophical and conceptual value. String theory has pushed the boundaries of our understanding of the universe, prompting new questions and insights about the nature of reality. Scientific progress. Science often progresses by pushing the limits of what we know and can test. Even if string theory itself doesn't provide direct benefits, it might pave the way for the next theory that does. In conclusion, while the claim about string theory's lack of testable predictions and tangible benefits holds true currently, it doesn't necessarily diminish the value of the theory as a part of the scientific quest to understand the fundamental nature of the cosmos.
Design a testable prediction of string theory that I can perform at home to either support or falsify the claims made in string theory.
String theory operates at energy scales and dimensions that are far beyond every human experience and capability of technology. Its predictions often involve the behavior of fundamental particles and forces at scales that are only accessible through high-energy physics experiments, such as those conducted at facilities like the Large Hadron Collider, LHC. Creating a home experiment to test string theory would be like trying to detect radio waves with a chocolate bar. The tool simply isn't sensitive to the phenomenon you're trying to observe. To test string theory, you will need equipment that can probe the Planck scale, or quantum gravitational effects.
I mean, that's like your opinion, man. All right, moving on. That's where my mind is now. Okay, no more tangents. Unless it has to do with the Euclidean distance. Where A and B are two n-dimensional vectors. Oh. Yeah, so in here, A and B are vectors, and they can be any across any dimensions. A vector is just a array. It's just a indicates motion between one area in space to another. So if you have two dimensions, then a vector could be from here to there. But if you have three dimensions, 4, 5, 6, vectors aren't limited by you can do it for any dimensions. And the other thing to note is these aren't necessarily dimensions of space. We can see, actually in this case, what they are is dimensions of our data set. So the first one is number of ports used, number of VLANs is the second, number of VRFs, and number of ACLs is the last one. Okay, so in our example, the observations for our top of rack switches, we have the Manhattan distance. In this case, the distance is calculated as the sum of the absolute value of the difference of the different vector dimensions, which effectively means the distance as if a grid-like path was followed between the 2 points. So here's the Manhattan distance. Okay, so the Manhattan distance would be the total length through space as the of the vectors. So we've got our number of ports used here, number of VLANs used. And the other thing that's interesting to note is it looks like the numbers get smaller. So here is like you have fewer ports being used than here. And then here it's the opposite. So let's look at the Manhattan distance. So the Manhattan distance is the absolute value of P1. Actually, no, this is just a point. So I think, I don't know. So P1 minus P2, the absolute value of that, plus the absolute value of V2 minus V1 equals the Manhattan distance. The general formula in this case would be this. And it's just a little bit beyond me now. I haven't really done a lot of math lately. Actually, on the channel, I did second grade math. But I have taken, college level calculus before. I just never. I don't think I passed it.
The image you've uploaded describes Manhattan distance, also known as taxicab distance or city block distance. It's a way of measuring distance that only considers vertical and horizontal paths, like navigating the grid-like pattern of streets in a city such as Manhattan. Instead of drawing a straight line from one point to another, which is how we usually think of distance, the Manhattan distance measures how far you'd have to walk if you could only follow the city blocks, first walking along the avenues vertical direction, and then along the streets horizontal direction, or vice versa. The formula shown sums up the absolute differences of the corresponding coordinates of 2 points. The absolute value makes sure you're considering the total distance without worrying about which direction you're going. If you were to use this in a real-world setting, say you were at the corner of 3rd Avenue and 15th Street and wanted to get to the corner of 5th Avenue and 10th Street. Instead of flying straight there like a bird, which would be the Euclidean distance, you'd walk 2 blocks over to 5th Avenue and then 5 blocks down to 10th Street, for a total of 7 blocks. This total is your Manhattan distance.
Yeah, so tell me how this is different than the Euclidean distance. Show me the formulas for each and break down which each part of the formula means and what the symbols in the formula mean more broadly, and explain the difference by showing me the differences between the two formulas. This is a lot for me to be doing late in the day. I'm about to go to sleep.
Certainly. Let's break down both types of distance measures using the context of a simple two-dimensional space, like a flat piece of paper, to make it easier to understand. Euclidean distance. Formula. x2 minus x1, 2 plus, y2 minus y1, 2, sqrd, x underscore 2, x underscore 1, squared plus, y underscore 2, y underscore 1,
what?
squared, x2 minus x1, 2 plus, y2 minus y1, 2. Breakdown. x1, y1, x underscore 1, y underscore 1 by 1, y1. The coordinates of the first point, like where you were starting from. x2, y2, x underscore 2, y underscore 2 by 2, y2. The coordinates of the second point, where you want to go. x2 minus x1, x underscore 2, x underscore 1, x2 minus x1, and y2 minus y1, y underscore 2, y underscore 1, y2 minus y1. These calculate the horizontal and vertical distances between the points. x2 minus x1, 2, x underscore 2, x underscore 1, squared, x2 minus x1, 2, and y2 minus y1, 2, y underscore 2, y underscore 1, squared, y2 minus y1, 2. Squaring these distances ensures they are positive and also correspond to the areas of squares if we think the distances as sides of square.
Ugh.
SQRT, taking the square root gives us a straight line, diagonal, distance from one point to the other.
Yeah.
Manhattan distance. Formula. Divides x2 minus x1 plus y2 minus y1 divides x underscore 2, x underscore 1 plus y underscore 2, y underscore 1 divides x2 minus x1 plus y2 minus y1. Breakdown. Divides x2 minus x1 divides x underscore 2, x underscore 1 divides x2 minus x1 and divides y2 minus y1 divides y underscore 2, y underscore 1 divides y2 minus y1. The absolute value of the differences gives the total distance traveled along each axis independently, only horizontal and vertical, no diagonal. Plus plus plus. Instead of combining these differences into a square and square root like in Euclidean distance, we just add them up.
Yeah.
Differences between the two. Path taken. Euclidean distance is the shortest path and is like drawing a straight line between 2 points. Manhattan distance measures as if you're walking along a grid and can only move horizontally or vertically, not diagonally. When to use. Euclidean distance applies to, as the crow flies, scenarios or direct paths in open space.
Yeah.
Manhattan distance is useful in grid-based navigation like city streets or board games. Visualization. If you had a map and drew a straight line from one point to another, that would represent the Euclidean distance. For the same map, if you drew a path that follows the grid lines, like the moves of a rook in chess, turning at right angles only, the length of this path is the Manhattan distance. In essence, the Euclidean formula combines the horizontal and vertical distances in a way that considers the direct path through space, while the Manhattan formula considers only the sum of these distances along their separate axes, mirroring movement on a grid where diagonal movement isn't allowed.
So if you're in a flat place like Ohio and you're in a hilly place like Seattle, could you use the same formulas, or would you have to account for that extra factor of the steepness of the hill you're on, or whether it's just completely flat?
In a perfectly flat place like a typical Ohio landscape, you can use both the Euclidean and Manhattan distances with the assumption that you're moving across a flat surface. These formulas assume that there's no difference in elevation between any 2 points. The Euclidean distance would give you the straight line path between 2 points on a flat plane. The Manhattan distance would give you the total distance moving in orthogonal, right-angled paths, which is still applicable on flat grid-like layout, such as city blocks.
Oh, you would have to add another dimension. Okay, so you just add it there.
However, in a hilly or mountainous place like Seattle, you'd have to consider the terrain's elevation changes, which add the third dimension to your calculations. For Euclidean distance, you'd have to use the three-dimensional version of the formula. x2 minus x1, 2 plus, y2 minus y1, 2 plus, c2 minus c1, 2, sqrt, x underscore 2 x underscore 1, squared plus, y underscore 2 y underscore 1, squared plus, c underscore 2 z underscore 1, squared, x2 minus x1, 2 plus, y2 minus y1, 2 plus, c2 minus c1, 2. Where z1 z underscore 1 z1 and z2 z underscore 2 z2 represent the elevation at points 1 and 2, respectively. This would give you the straight line, as the crow flies, distance accounting for elevation changes. For Manhattan distance, if you're thinking about walking or driving, the formula becomes a bit more complex because you can't simply add a straight vertical distance to the sum. You'd have to consider the actual path you'd take up and down the hills. Realistically, you would measure the distance along the path you would travel on the streets, which would zigzag up and down the terrain. This isn't a simple addition of absolute values anymore because the steepness of the hill, gradient, would affect the distance you cover vertically. In hilly terrain, neither the Euclidean nor the Manhattan distance would directly correspond to the actual distance you travel. For accurate measurements, you need to use a path distance calculation that takes the gradient into account, often requiring detailed geographic data and more complex algorithms such as those used in Geographic Information Systems, GIS. These systems can calculate the cost of moving across terrain, taking into account not just distance but also the effort required to ascend and descent, which is far more representative of the actual experience of moving through hilly landscapes.
Alright, so let me see here. Okay, so the general formula in this case would be this. So it's changing the Manhattan distance formula to a general formula applicable to this case. So the general formula applicable to this case would be I is a bad, I wish, so index, it'd be the index. So through n. So as that goes up to n in a continuous fashion, it's the absolute value of a of the index minus b of the index, which is difficult because there's no a and b on the graph. This is all over my head. Oh yeah, a and b are two n-dimensional vectors. Okay, so the next part is cosine distance and cosine similarity. Oh my lord. This is kind of a lot. You know what? I'm almost... Oh. Let's get to the key takeaway. Yeah, let's get to the key takeaway, and then that'll be it for now. I think taking a bit of time with this makes sense. So let's get to the key takeaway, and then end the video. So the next one, and what I mean by one, the next the next type of distance used in the context of a machine learning algorithm is cosine distance. Other forms of distance used in the context of machine learning algorithms are Euclidean distance, Manhattan distance, and the final one that we will read about right now which is cosine distance, and cosine similarity. In this case, the focus is on the angle between the two vectors. If the angle is very small, the two vectors are considered very similar, and the cosine will result in 1. This is referred to as the cosine similarity. The distance view is cosine distance equals 1 minus cosine similarity. And remember that the cosine similarity is an angle that is so small that the two vectors are considered very similar, and the cosine will result in 1. So here's a graph of that, very clear. I can't imagine anything about this being difficult to understand. This kind of looks like a kindergarten drawing.
This image illustrates the concept of cosine similarity and its related measure, cosine distance, which are methods used in various fields such as data analysis, information retrieval, and machine learning to measure the orientation and not the magnitude between two vectors in a multidimensional space. In the image, there are two vectors labeled S111 and S222, originating from a common point, the origin. The angle between them is denoted by theta hat of theta. Cosine similarity. The cosine similarity is a measure that calculates the cosine of the angle between two vectors.
This means angle.
It's given by the formula cos theta, which is the dot product of the vectors divided by the product of their magnitudes, lengths. This measure is bound between -1 and 1. A cosine similarity of 1 means the vectors are pointing in exactly the same direction, -1 means they are pointing in exactly opposite directions, and 0 means the vectors are orthogonal at a 90-degree angle to each other. Cosine distance. The cosine distance is related to the cosine similarity and is given by the formula 1 minus cos theta, 1 cos theta, 1 minus cos theta. Unlike the cosine similarity, the cosine distance measures how different the directions of the two vectors are. A cosine distance of 0 means the vectors are in the same direction, identical, and a larger cosine distance indicates more difference in direction. This measure is often used in situations where the magnitude of the vectors is not important, but the orientation is. For example, in text analysis, it's used to measure the similarity between two documents represented as term frequency vectors, regardless of their length. In the graph, the two axes could represent features of data points, such as the number of times certain words appear in two different texts. The cosine distance would tell you how similar the documents are in terms of words they use, without considering how long the documents are.
Interesting. So you could tell how similar the words. Okay, so let's talk about that. So the cosine distance, that it would tell you how similar the two documents are in terms of words they use, and without considering the length of the document. So can you give me like two documents in English that have the largest cosine distance, meaning that they use basically little to no of the same words?
Sure, imagine you have two documents. Document 1, a recipe for chocolate chip cookies. This document contains words like flour, sugar, chocolate, oven, mix, bake, etc. It's all about the ingredients and the process of making cookies.
Cool.
Document 2, a technical manual for a smartphone. This document uses words like technology, screen, processor, battery, resolution, instructions, warranty.
That makes a lot of sense to me now. Alright, so there are other distances I will not elaborate, like Minkowski distance, Hamming distance, used for text primarily, and others. I want my own distance. Give me a distance. I have to invent one. Okay, so there are other kinds of distances. There's Minkowski distance, there's Hamming distance, which is used for text, and then there are others. Invent a new distance and write out the formula for it. And credit it to me. Contextual overlay distance.
Let's have a bit of creative fun with this. I'll invent a distance measure called contextual overlay distance, COT. This distance measure is designed to evaluate the similarity between two pieces of text, not just by the words used, but also by the context in which they're used, which is something traditional text distance metrics don't typically consider deeply.
Thank you. Here it is.
Contextual overlay distance, COT. The idea is to combine semantic analysis with word frequency to provide a more nuanced measure of text similarity, taking into account the context. Formula. COT A B equals 1n area summation I equals 1n FAI minus FBI 2 plus lambda dot operator 1 minus SC I by COT A B equals frac 1n. Sum underscore I equals 1 caret n f underscore a underscore I f underscore b underscore I squared plus lemma cdod 1 s underscore c a underscore I b underscore I cot a b equals n1 I equals 1 n fai minus fbi 2 plus lambda dot operator 1 minus sc I by where AAA and BBB are two documents. NNN is the total number of unique words in both documents. FAIF underscore A underscore I FAI and FBIF underscore B underscore I FBI are the normalized frequencies of the EDH word in documents AAA and BBB respectively.
Yeah, I don't know enough about it to know if it's. I think a lot of times what it does is it'll like create a new symbol. And it'll just say like this symbol is the thing you would need to define to have it meaningful. So it's like, it comes up like this. It's like meaningful equation equals x plus y plus the thing you come up with that makes it meaningful. We're going to call that Z. I feel like ChatGPT does that a lot when you ask it to invent new math and science. Okay. So there we go. However, now the critical question is, which one applies to your use case? Euclidean distance tends to be the default option unless there are specific reasons to use another. For example, for anything related to text processing or in general non-numeric characters turned into numbers via some kind of dictionary. The results are vectors where each dimension represents one such category. Cosine similarly tends to be more adequate for this type of scenario and particularly very popular in any NLP or recommendation system use cases. When the vector dimensions correspond to very different characteristics, the Euclidean distance could skew the results, so it may be preferred to use the Manhattan distance. In our top of rack switch example, we will use Euclidean distance. There is another problem. It is not inherent to distance measurement, but is associated with it. While I have not described the clustering algorithms yet, you already know that the distance between the observations determines the clusters and whether an observation belongs to one or another. In order to determine the distance, let's assume Euclidean for now, we will compute the difference between the values on each of the dimensions for the two vectors to compare. However, what happens if the range from one dimension, let's say P, is between 10 through 20, and the range on the other dimension, let's say V, is 2000 through 3000? That means that even if the relative difference on P is significant, with relatively small differences in V, the distance calculation will be highly biased towards the V dimension. Basically, each dimension's scale matters, and it is particularly relevant for clustering problems. That kind of makes sense to me, actually. Therefore, we need to rescale the values to make them more comparable. So the key takeaway is any concept in machine learning needs to be expressed in numbers or quantities. When we talk about similarity, we need to translate it into formulas that can express such a quantification. All right, so I've created a number of bookmarks. If I'm deep in thought in something, the last thing I want to do is lose my place. So delete all the old bookmarks here. I don't think there's a faster way to do this. All right, so when I come back, we'll be doing more of this sort of thing. No graphs anymore, but we've got a lot more. Oh, we do have some graphs to get through, so stay tuned for good times.